So, hey everyone, I'm Andre, and I'm here to present um, my latest paper, SynCoGen, which is synthesizable co-generation, synthesizable 3D molecular generation via joint reaction and coordinate modeling. Um, so let's get right into it. Um, so the landscape of all atom 3D molecule co-generation is um, such that there's a lot of models that design both atoms and bonds and coordinates. Generally, cogeneration for small molecules works quite well, but in practice, when molecules are synthesized, they're not made atom by atom. We purchase precursors, and chemists know a set of or are familiar with a set of medicinal chemistry reactions that are commonplace and very high yield that they use to combine these building blocks. And building blocks are just highly functionalized small molecules that are flexible to making a lot of different kinds of small molecules through combination or coupling via these reactions. So a lot of the contemporaries of these 3D molecular co-generators that operate at the atom level, like Semlaflow and Jodo, and since the initial submission of this paper, there have been a lot more. Um, they generate atom types and coordinates, and it's difficult to zoom out and sort of guarantee that these synthesis pathways are valid at a synthetic chemistry level without building block level constraints or building block level training. So our approach to trying to address this problem was a model called SynCoGen, and the idea was, can we take this all atom discrete and continuous simultaneous diffusion approach and apply it to the building block level instead? Oh, how did that happen? Okay, so in order to do this, of course, we had to curate a new data set. So we do this with and provide a set of around 600,000 molecules and reaction pathways and around 3.4 million low energy conformers from a relatively small set of 93 building blocks and 19 reaction templates. So we kind of generate these molecule sets combinatorially, and we do 3 to 5 building blocks per molecule. And with our trained model, we're able to use it for a bunch of cool tasks like 3D molecule generation unconditionally, and also fragment linking and pharmacophore analog generation. So if we think about what we want to go into a molecular graph, of course, these previous works rely on atoms connected by bonds. This is the most straightforward formulation of a molecular graph. But again, it's hard to constrain the precursors this way, so we want to sort of zoom out and have a more coarse-grained molecular graph with building blocks connected by chemical reactions. And this better reflects experimental synthesis considerations, but we're not quite done yet with a formulation like this. In general, naive representation was just one building block as a node and one reaction or bond formed by a reaction, more accurately, is an edge. It's not quite sufficient to describe a unique molecule, even if we're not considering stereoisomers or chirality. So, for example, if we look at something like this, or any building block for that matter, that has more than one identical functional group that can react. So here we have an amine group. If we couple this to a compatible building block, a uh, typical building block reaction graph, like I've described earlier, can't tell us which amine group is occupied unless we provide some explicit notation or consideration for the number of reaction centers on a molecule and label them with which is which. So this helps us arrive at our dataset generation method, which is simply this repeating set of steps where we would select a building block, a reaction center on that building block, um, a compatible reaction with that reaction center or that functional group, and a compatible second reactant to couple with that building block. Do this 3 to 5 times, and you have a molecule. And as you annotate these molecules with these building blocks and reaction centers, you're able to sort of build this synthesis graph that comes along with the coordinate generation. So you end up with 600,000, or we ended up with 600,000 synthesizable molecules and their reaction paths, as well as conformers generated with XTB. Um, and what this looks like a little bit more formally is a molecule is we format them as one hots over building block identities and reaction identities. And in order to keep these reaction centers in the information encoded by the reaction matrix. So here n is the number of building blocks in a molecule. We basically flatten a triple that encodes the reaction and the attachment point on the incoming and outgoing building block. So if there's a reaction between building blocks 1 and 3, we also encode the reaction along with the reaction type. We encode the reaction center on building block 1 and the reaction center on building block 3, just to make sure that our graph representation fully specifies the molecule without any ambiguity. And of course, we maintain 3D coordinates as well. This is reasonably straightforward. M is sort of the upper bound on the total number of atoms in any molecule in our data set. I'll get into how that's constructed a little bit later. So now that we have a graph formulation for building blocks and we have our coordinates as they would be done normally, we can get into how exactly we train such a model. For coordinates, we can simply use vanilla conditional flow matching. There's not too much to say about that. And with building blocks and reactions, these are discrete categories. There's been a lot of work on categorical diffusion models, and the formulation we use is an absorbing state masked diffusion approach. If you're not familiar, essentially, instead of using a rate matrix and sort of a CTMC style jumping between categories, the only transition that happens is to and from a sort of masked token or masked building block index. So you can see here at time t equals 1, so here we're using the diffusion time formulation. You can see here at t equals 1, all of our building blocks here, there are 5, are masked, and all of our reactions in gray are masked as well. The diagonals are hardwired to no edge because there's no reaction from a building block to itself. And as we denoise over time and get closer to t equals 0, the mask tokens sort of flip to individual building blocks and reactions until we have a graph that fully specifies a molecule. So we use the simple and effective mass diffusion language model flavor of mass diffusion. This is an absorbing state mass diffusion model that comes with a couple of really simple simplifying assumptions. One is that once one denoises a building block, it is fixed for the whole sampling trajectory. So that corresponds to the top condition where ZT does not equal M, so ZT is not the mass token in the equation on the right. And there's a 0 likelihood of remasking. So all that means is once a building block is denoised, it can never be remasked during sampling. These assumptions actually provide a nice way to relate a negative log likelihood to the diffusion loss, but we don't have to care about that here. So what
Yeah,
this looks like, oh, sorry, go ahead.
I- yeah, we have a question. Tranyan, do you want to ask your question?
Yeah. You're muted.
Yeah, I think Tranyan is muted. Maybe we can continue, and if there's question, he can type in the chat.
Okay, I'll monitor the chat and make sure I don't miss the question. Um, yeah, so I'll keep going for now. Um, so the generation process for SynCoGen in total looks a little bit like this, where as building blocks are denoised, it's actually relatively simple to um, have a corresponding change in atom identities. Um, you can think of it as denoising atoms in groups. So once a building block is denoised, we know exactly what the bond orders of all its constituent atoms have, and also their identities. And so as we get closer to the end, fewer and fewer atoms take on this ambiguous mask identity, and we start to have these disjoint fragments. And as we denoise reactions that describe how these building blocks bond. They connect with each other, and at time t equals 0, we have a full molecule. And also via the denoised graph, we have a proposed synthesis pathway. When we train a model like this, we need a couple of considerations. So this is all well and good, but there are a couple of things that we need to get out of the way that sort of depart from an all atom formulation. One is that we want to support variable atom counts. Now, typically in these unconditional molecule generators, during sampling, you have a prior over the number of atoms so that you can specify before any sampling is done, maybe according to the data distribution in, I don't know, Geome Drugs or QM9 or something, just the number of atoms and how likely each number of atoms from, say, 20 to 60, um, how likely that number of atoms is to show up in the dataset. We don't really want to do that here. I think we want it to be a little bit more ambitious and say, okay, if we instead specify the number of building blocks, can we remain flexible to the number of atoms in each building block as we go forward, just to allow the model a little bit of flexibility downstream in terms of um, conditional generation or fragment in painting. So even with a prior over the number of building blocks, the atom count would vary. And so what we wanted to do was start with an upper bound on the possible number of atoms in any building block in our data set. And as we denoise building blocks and we discover which atoms we don't need from our sort of uh, superset of atoms, remove them over time during sampling. So, like I said, we should disregard these extra atoms during sampling as we learn which, or we select which building blocks that we are going to be using in this sort of mass diffusion framework. And we want to construct a training regime that corresponds to this dynamic mask where the number of atoms that we consider differs depending on the amount of information that we have. And so it looks a little bit like this, what we came up with. Basically, we have on the top here, we have a um, pretty straightforward interpolation. So with flow matching, of course, you are interpolating your data example with some sample from a 3D Gaussian for molecules most of the time. And so we see that on the top, once a molecule is fully noised, we have these extra atoms from a Gaussian prior. And at this point in sampling, we wouldn't know what this building block would become. So the number of atoms here is greater than the number of visible atoms once the building block has been denoised. And what this looks like when we construct training data pairs is when a building block is not selected, we keep the extra atoms in the ground truth. And what this helps us do is encourage the model to discriminate between real and extra atoms at every sampling step, not just the steps where the building blocks are denoised. Here we fix the extra atoms in place. So what the model is learning to do, we hope at the time, was reassemble essentially the true atoms of the molecule while selecting specific atoms to fix in place and disregard for sampling. And we find that in practice this works quite well. There's a question from Trung Nguyen.
Yes. So how can you select the building block? Like, is that residue in the protein or is that like chemic chem? Yeah. How can you select the building block?
Oh, in general, you can take them from enamine. It could be technically a residue in a protein, but we're working with small molecules, so these are just a general highly functionalized like fragment of a molecule that works well when combined with other fragments via these reactions. So we don't use necessarily residues here. We just have a set of building blocks that are cheap that you can buy from vendors.
Oh, like someone provide to you, or is there any like guideline for choosing building block?
Um, so our criteria for these building blocks in particular, it's a good question. I don't actually have it written down here, but
Uh-huh.
um, I there's a chemist on my team, and we basically filtered a set of building blocks that we know were commercially available for a price of under, I believe, $200 per gram. I think that it was. And then we selected those that were a set of around 100 that were reasonably flexible, so that could generate a reasonable diversity of chemical space, um, and also were unlikely to be toxic or anything like that.
Oh, I s-
Yeah.
I have one more question, maybe
Yeah.
because so you generate like 3D structure and like uh, but I know that the protein can be characterized into like primary structure, secondary structure, tertiary structure. And if I interested in generate secondary structure, for example, can the model generate that?
Um, so at the moment, we haven't tried generating proteins
Oh,
with the model. Proteins are definitely a bigger drug class than small molecules, and I think at the atom level, we might encounter some growing pains with scaling.
mhm.
Um, just because there's so many more atoms. But
I see.
at in general, the extent of the uh, geometric, I guess, spatial information of the model is limited to just the placement of the atoms. So just the position of atoms in space, and informed by the identities of the building blocks, but it doesn't model anything past or on a coarser grain, spatially than the positions of individual atoms.
Um, I
Okay.
have two questions. One is
Okay.
like, why do we only pick 93 building blocks? Like, for example, for Animate Space, like it has like a lot more building blocks, and those are also like kind of chemically like cheap to make.
Yeah.
Yeah, it's just like a issue of like kind of combinatorial search would have like a computational limit or
So this was basically our initial set. Like we wanted to, the short answer is we started with this sort of proof of concept set. And since it generated a reasonable diversity, once expanded combinatorially to a few million molecules, we just kept it that way to run our basic experiments. Um, we are working on generating a much bigger data set kind of right now to sort of scale the model building block wise. But this is just our proof of concept set, and we thought it was still interesting to perform all of our experiments on with this smaller set.
okay, yeah, and another question is, so I know, like in how the data set is generated, like you use reaction templates, so kind of saying like, if this does happen, like that would be like the product it makes, but, like how do you guarantee kind of in reality, like it actually chooses that reaction to happen when there are like multiple reactions possible at every step?
I'm not sure what the are you talking about in the lab
Yeah,
or
just like in kind of like in silico, like how do you guarantee kind of each step is exactly like what it's gonna choose to happen as reaction?
um sorry, I'm still not quite sure what you're asking. Are you saying are you asking how do I guarantee that building blocks and reactions are compatible with each other?
Um,
Or
Yeah, I'm not that familiar with chemistry, but just would there be cases, for example, like say if you pick this reaction center and this reaction template, like then they would undergo this reaction and produce this thing. But it seems like that requires in silico like 100% like that is what is gonna happen. Would
Mhm.
there be cases say like there's chemoselectivity, so there are like competing reactions that could potentially happen at each step, like with like a probability instead of 100%.
Oh,
One.
okay. So, yeah, I see what you're asking now. Sorry for the confusion. So basically, um, in silico reaction simulations, they remove this kind of ambiguity. So there's no notion of yield or you know uh chemoselectivity or competing or like blocking groups. Um, a reaction uh in the language, I guess, in silico of RD kit, which is what we use for most chemical tasks, is basically just a query between the some functional group on one building block and a functional group on another. And if both of these queries sort of hit, so if you have two building blocks and the query for building block one on the reaction has a match on the first one, and building block two on the reaction has a match with the second one, then that's considered compatible, and the reaction in silico will proceed the same way. So what that looks like is it'll return a product that will proceed the same way every time. So that kind of ambiguity in RDKit and just in computational chemistry in general is not part of what we have to consider, thankfully. Does that answer your question?
Yeah, and is this like query hitting like one on the first another like on the second? Is it always like there's only one possible query at each step?
No. Which is why we have to select um the reaction center. So if there are more than one sort of match to each query, then that's why we want to maintain our representation where we select which reaction center or we record which reaction center that we select because we can pick, um, okay, if there's a query at atom, I don't know, 5 and a query at atom 9 that both match this reaction, which one did we pick? And that will help us fully describe the graph of the molecule and be specific to a specific molecule once we've constructed it.
Okay,
Yeah.
thank you.
Mm-hmm. Mansoor?
Hi, I had a question regarding the discriminator. This is a data pairing module. So
Mm-hmm.
you mentioned that this is like only used during the during sampling steps. So I was wondering like is it like already pre-trained or like what exactly is like inside this data pairing module? Is it like a simple classifier head or like how exactly does it work? Like in this scenario because like at each step so and does it the output also impact the next like step during generation as well, during sampling as well? Like,
Oh yeah, so sorry for being ambiguous about this. This is actually training. Th this when I say that this encourages the model to discriminate at sampling steps, um, I mean that this training formulation. So we actually apply this data pairing module at training time to our data, but we hope that uh, handling the padding atoms this way helps during sampling when we start from all masked atoms and we don't know which atoms are fully going to correspond to our molecule. That's what I mean. Does that help?
Okay, yeah. So like just to follow up on that note as well. So, like, so you like in your like main generators, they're like the vanilla flow matching, and then you have the diffusion for these building blocks like generation. So where exactly like in the architecture does this like discriminator fit to do the right padding like it like specifically like is it like a classifier head or something, or what kind of loss is it
Yeah.
optimizing? Yeah.
No, it's not actually a discriminator. It's maybe I shouldn't have used the word discriminate because that implies that there's classification involved when there isn't.
Okay.
When I say discriminate, I'm more so referring to the fact that because we are encouraging through this data pairing, we encourage the model to pick some atoms to reassemble and some to leave alone. This will also happen during sampling, and so the model can be discerning as to which atoms that it decides should reassemble and which atoms should be considered padding and ignored throughout an entire sampling run. So it's just a part of uh the the model prediction coordinate wise is just ground truth coordinates every time. There's no classifier or discriminator in the model. Um, so that's my fault for not being more clear about that. But that it's just simple flow matching. There's no additional heads for that.
Thank you. Yeah.
Okay. So moving forward, I guess the losses um pretty straightforward for graphs. We just take the negative log likelihood for the true building block or reaction index, um, and we calculate that on the logits outputted by the model. This is pretty straightforward, like I said, but this is actually the same as uh, the for discrete diffusion as the continuous diffusion loss. Um, again, as showed by the simple and effective mass diffusion paper. For coordinates, simple mean squared error between predicted and ground truth coordinates. All of these are time weighted, by the way. We also add some auxiliary losses to help out with prediction. We find that they help considerably. So, for instance, a pairwise distance loss. So, for atoms that are within a certain distance threshold in the ground truth, we add a term to penalize how far apart they are relative to the ground truth in the prediction. And also things like bond length loss and smooth LDDT losses. You might recognize this if you work on proteins. They improve model performance as well. So for a model diagram, we borrow from SemlaFlow, which is an equivariant model for atom-based. So it's actually an all-atom model. I'm not going to go fully into the architecture um, for this. It's just an E3 equivariant model, and it handles invariant information like atom types and bond types, and equivariant information like representations of coordinates and relative coordinates as well. And they communicate through pairwise messages. We actually don't modify too much with SemlaFlow. All we have to do, we find, is to replace the output heads to instead return a set of logits over our building blocks and a set of logits over our edges, and the coordinate prediction can sort of proceed as usual. So what you might notice though, input and output wise, is that we don't actually change the inputs. We still are feeding information to the model at the individual atom level and at the individual bond level. And the reason for this is because it's actually pretty simple to broadcast your building block information to atom information. Like I was mentioning earlier in the diagram of the model, you can essentially have an index or a special token for masked atoms or masked individual bonds between atoms. And if a building block is unmasked, you just take the true atoms and bonded entities in a sort of a one-hot way to throw to your encoder. And if it's masked, you pass the sort of masked index into your encoder. So you do this at the atom level after broadcasting or converting up to the all atom level from your building blocks or whatever partially masked building block state you have for your molecule at the time. So for inference, what this looks like, and I've mostly described this already, but you sample an upper bound on the number of atoms in each building block in our library, and you take, you don't sample it, you pick that many atoms, and you take a Gaussian prior and sample from that with that many atoms, uh, and take less than the total number of building blocks in any molecule that you choose. We pick five. And so that is our prior over the number of building blocks for, and this just corresponds to the proportion of examples in our data set that have that many building blocks. And then once each building block is denoised, we masked out the extra atoms in all subsequent steps. We no longer have to consider them as true atoms or potentially true atoms, and then recenter. So one thing about equivariance, as you can imagine, is that with respect to the molecule itself, so obviously with respect to the all the particles in the model, which include padding atoms, um, we don't change anything about equivariance. It's still E3 equivariant. But with respect to the actual molecule, only after all the building blocks have been denoised and no padding atoms remain in the model, does the centered molecule, is it equivariant, basically, with respect to the molecule. Because before that, the padding atoms sort of participate in centering and have weight in the model and break that sort of rotational and translational equivariance. But we find that despite this, the model actually still works quite well, even though we only have this sort of notion of partial equivariance as we continue to denoise building blocks. So we keep the equivariant architecture and we use it for most of our experience. So even more considerations because even though we have a non-autoregressive framework and it lets us do all sorts of cool things like denoising building blocks out of order or doing disjoint fragment linking, we still would like to constrain it with what we know. So if you're not familiar with how synthesizable molecule generators that happen sort of autoregressively work is that you have this added benefit of since you know which building block you're attaching the next building block to, or you know which molecule you're attaching the next molecule to, you can explicitly filter for reactions that are compatible with the current molecule that you have, and same with building blocks. So you are essentially never going to encounter a situation where you are generating invalid molecules, at least according to the reactions and building blocks you have at your disposal. Since we're not doing that here, and it's stochastic in the sense of we don't have control over which building blocks and reactions are denoised first, um, we can denoise in any sort of order. We still want to include some notion of compatibility. And so our surrogate for this is given some denoised reaction or building block. Let's say we denoise a reaction between building block 1 and 3. We now know that building blocks 1 and 3 have to correspond to that query that the reaction describes. So we can limit sort of the reaction identities or the building block identities at building block 1 and 3 to only those that match that query. And so this is just this partial compatibility guarantee, but it actually works very, very well in increasing the validity when we ablate on it in our experiments. So another thing is that we only have linear molecules, so no cyclization reactions, no macrocycles or anything like that. And so because we assemble our molecules in practice in our training set, sort of one molecule or one building block at a time, we know that, for instance, building block 2 is only going to have one incoming edge. There's not going to be some other building block that's connected to building block 2 because building block 2 is picked after building block 1. And if it if something was picked after building block two, it would have an outgoing edge to that building block. Um, so with these extra assumptions, knowing that each building block is attached to at most one previous selected building block and trying to um, constrain to chemical compatibility, we can actually make molecular validity a lot more easier and not force the model to learn things that we already know. So now, oh yeah, do you always mask the last n atoms for a building block? Does your model predict each atoms? So the question was, do you always mask the last n atoms for a building block, and does your model predict each atom's presence or absence independently? Um, no. So the presence or absence of an atom depends entirely on the masked diffusion uh, denoising a building block. And so if a building block is picked with 11 atoms, for instance, and the maximum number of atoms in any building block is 16, the last five will be masked, or I guess masked out. I say masked out because masked would correspond to the state where we don't know what the building block is, and therefore all 16 atoms in that building block would be considered masked. But once the building block is denoised, those final five atoms would be considered invalid, essentially, or no longer considered as potentially valid atoms, if that makes sense. Does that answer your question, or?
I guess what I'm getting at is if you are trying to consider the relative positions of those atoms within the building block, but you're always masking the last n positions, and I'm just assuming that based on the schematics that you've shown. I don't know, like is there some sort of relationship between the relative atom positions that maybe is sort of strange when you're sampling? Does that make sense?
Can you ask that one more time?
So
I'm
you
trying to
have
get a
like
sense of
this,
it. Yeah.
yeah, so you have like this Gaussian for all your atom positions, but it looks like in
Right.
these schematics that you're always picking the last n positions to be padding rather than actual
Yeah.
atoms.
Yeah.
But when you're sampling or something, and your model is trying to sort of place these atoms over time, um,
Hmm.
and it's trying to sort of like determine which atoms are going to be present or not present in the final structure depending on what building block you pick. Is there,
Yeah.
I don't know, like is there would there be benefit in predicting each atom's whether it's padded independently or sort of allowing that to be random so that the atom positions could flow through better, or the model could sort of pay attention to relative positions and figure out which ones might be present in that final structure?
Honestly, yes, it could be. I thought about this before too. I see what you're saying because if you have a little bit more control over like if we continue this thought experiment, what you would want to happen, I think ideally with this flexibility is you would be able to pick some atom, right? That's not it's like far away from your other atoms in that building block. So you could say, okay, maybe the some atom in the middle of this building block is not going to correspond to the final one because it has to go so much further um, to reassemble into this building block. So you could do some kind of like optimal transport stuff, and you um, could kind of pick your padding indices with a classifier or built into whatever model you already have, and then just decide dynamically based on what would be what would make the most sense just transport wise. Um, we find that we don't have to do this in practice, but it's definitely worth exploring going forward. And I would say that it like hmm, I would say it's not necessary, but I think it would improve performance somewhat if done correctly. Yeah.
Makes sense. Thank you.
Yeah. Um, okay. So for unconditional generation, we're getting into our experiments now. Nothing too crazy here. This is just a few building blocks. So there are graphs on the left and there are conformers on the right as sampled from our model. Um, these are somewhat on the bigger side, but they help demonstrate the capabilities of our model to generate reasonable conformers even for molecules that are on the larger side. So in general, SynCoGen actually does quite well compared to other models in terms of validity and also in terms of general energies. A little bit worse in terms of novelty, but that's because our sort of proof of concept data set was a little bit small in scope, but still pretty good. Here, AI Synfinder and Synthesius are just sort of computational retrosynthetic planning tools, and they attempt to take a molecule and decompose it tree-wise into purchasable building blocks in a set that they sort of have um, access to via reaction templates um, that they have sort of programmed into them. So if each of these are calculated for around 100 molecules, so the number here for AI Synfinder and Synthesius corresponds to the number of valid synthesis routes found. For a visual version of this, we can kind of see that for RDKit validity, SynCoGen does really well. And also for Synthesius solve rate, we find that SemlaFlow is the best sort of uh, benchmark compared to the rest. So what we do is we retrain SemlaFlow on our molecules to sort of see if the an all atom model can recapitulate the kind of chemistries that we want it to capitulate without actually being enforced. And we find reasonably that it's not able to do this. And even though this is what you might expect, I think this is still a reasonably significant result because it sort of motivates the SynCoGen framework in a way that um, despite training on molecules that are synthesizable in the way that you want them to be as defined by your reaction and building block vocabulary, all atom models still have a problem where they will sort of interpolate in ways that harm the validity and the um, synthesizability of the molecules that they generate. And so here are some ablations. I only added this to sort of include or to mention from earlier that these constraints really improve the performance well. So I haven't tested all of the other improvements without the constraints, but without any sort of things like auxiliary losses or self-conditioning, without constraints, the validity of the molecules are somewhat poor. This might honestly be a limitation of the model itself. Um, I am not entirely sure what how much I should reasonably expect the model to be able to learn about chemical compatibility without any constraints. But with them and with self-conditioning and auxiliary losses like bond and smooth LDDT loss, the validity becomes quite high. Um, and here's one experiment that becomes possible when you're not working with autoregressive sort of models is this disjoint fragment linking. And we find it to be pretty interesting because you don't actually have to retrain the model at all from just this generic unconditional generation sort of training. And it's able to take two fixed fragments. So here we select two PDB proteins with ligands that have building blocks at each end that correspond to building blocks in our data set. We clear out the middle and we use SynCoGen to generate linkers for them. Here, the protein is strictly for visualization. We don't actually condition on the protein here. This is a very, very simple and bare bones fragment linking experiment. And we can see at the bottom that each molecule does have a synthesis route as well. So once we have this molecule generated, we again have access to this proposed synthesis route that should make it more straightforward for chemists to make the molecule in practice. And we find again that we're able to achieve decent validity. Again, not ideal because it's not retrained on the task, but over 50% on 2 out of the 3 um, for validity and much better energies than difflinker. We fine tune also for a few epochs, and we find that validity increases reasonably significantly as well. Just in general, I think that if we include fragment linking into the training set, I think that validity would increase a lot more. But here, these are just lightweight experiments that don't necessarily require full retraining of the model to do fragment linking. And I think that if the molecules are synthesizable, validities of 70% or 60% are actually pretty reasonable because for a molecule like difflinker, or for a model like difflinker, if none of the molecules are synthesizable, it doesn't really matter how many of them are valid according to RDKit. So finally, with the unconditional generation results out of the way, we move towards this pharmacophore analog generation. So this is our conditional generation model. We allow this basically with a modified version of the backbone that includes pharmacophore positions as sort of atoms in that are considered by the backbone but are never moved by them. We find that because our building block set is somewhat small, if we were to condition on all pharmacophores for every molecule in our training data set, again, we generate these pharmacophores using Shepherd, which is a really cool paper that both provides a model and a set of tools for generating pharmacophores and visualizing them. If we condition on every pharmacophore for every molecule in our data set during training, we tend to overfit to that. And what we do to mitigate this is we subset to about half the pharmacophores in each molecule, shuffle them, and train with those pharmacophores as input. And so our goal here is to find a way to approximate uh, like protein ligand generation by being able to recapitulate key interactions that each ligand has with the protein via its pharmacophores. And so because we set out to really see, even with our smaller building block set, whether these molecules that we generate dock reasonably well to a set of 10 protein targets, and we find that they do, which is a good sign. We compare our models to Synformer, which is sort of a 2D molecular generation that has synthesizability constraints. Shepherd, which provides a 3D model for generating small molecules, but not necessarily synthesizable. But it does include a pharmacophore conditioning module as well, which makes it a good point of comparison. And CGFlow, which is a autoregressive 3D generator that also includes synthesizability constraints in the model as well. And we see that we do quite well on most of the targets relative to the other methods. And so here's one intended or unintended consequence, or benefit rather, of having a smaller building block set, and that is that it's much easier for synthetic route finders because of the lack of sort of exotic building blocks or hard to purchase building blocks. If we're considering a larger building block set, it's much easier to find synthetic pathways. And so AI Synthfinder and Synthesius, we score much higher even compared to other synthesizable methods like CGFlow ZS and Synformer, just by virtue of having simpler building blocks in our set. Again, this still doesn't really, I would say this still is not worth the trade-off of having a larger building block set. So that's our top priority going forward, but it's cool to see. So here are basically just some examples. I wanted to include these just to illustrate that even when conditioning on a subset of pharmacophores for every molecule, we're still able to capitulate key things about both the shape and specific substructures that we might be interested in. So here is one example, and here is the PDB ligand 7-UVU for ClipP, or for the 7-UVU structure of ClipP rather. So like I mentioned, we really want to scale the model to around 10,000 building blocks and increase the dataset size to potentially 1 million molecules or 5 million or more conformers. We already have a dataset for this of graphs, and conformer generation is in progress for this. Another thing is that we touched on through the questions potentially peptide or protein generation, and because the SynCoGen framework could is designed to generate arbitrary building blocks coupled via arbitrary reactions, peptide synthesis actually falls within this framework. And so I think it would be an exciting direction to pursue to potentially do pharmacophore analog generation for small peptides as well as just general small molecule design with the building blocks that we've selected. Um, So SynCoGen, I think, has the potential to design analogs that are drawn from several therapeutic modalities. And the key thing here is that it uniquely guarantees this sort of adherence to whatever drug class we're interested in given our data set. And what I mean by that is, like we showed in the results earlier with SemlaFlow retrained on our data, even if we have some data set of molecules that are specific to one modality, there's no guarantee that an all-atom model would respect the chemistries or the vocabularies that we that we restrict the building block set to cover. But SynCoGen has this explicitly included in its design framework. And so being able to constrain your generation to whatever uh, vocabulary of building blocks, I think is a really strong thing and works well for both peptides and for small molecules. So in general, what you can do with a single trained SynCoGen model is zero-shot analog generation, which is pretty cool. You don't have to retrain your model to generate analogs via sampling and visualization. So compared to Synformer, for instance, you don't have to dock the molecule or generate a conformer before you can visualize the results because all of the molecules are generated directly in 3D and conditioned directly on 3D targets. Um, in practice, for drug discovery, often for very well-studied protein targets or well-studied ligands, one might want to keep some part of a ligand fixed, so you can condition on one building block or fragment in a specific place, and then different pharmacophores in other areas of the building block to try and iterate on a specific core. This is a popular sort of dilemma in sort of like mid-stage drug discovery after you've already generated your hits, or maybe you know the protein target a little bit better than you might have known it before. If you want to recapitulate key functional groups while leaving part of a molecule flexible, SynCoGen is capable of that as well. And again, you don't have to retrain the model to do this kind of hypothesis generation for molecules. And I think that's pretty cool. And I think SynCoGen generally represents a pretty promising sort of step towards synthesizable molecular design, particularly for these diffusion models that prior to SynCoGen only really operated at the all atom level. So yeah, that's about it. Um, I just wanted to thank my collaborators on this project, particularly Maruna Cretu and Chunghao Liu for helping me get over the hump and really sticking with me for all of the rebuttals and all the review processes. And if you're interested, the archive paper is linked, and so is the GitHub to our repo. So thank you so much for listening. Any more questions, I'll be happy to answer them. Mansoor?
Hi. Yeah. I had like a couple of questions regarding the flow matching and the diffusion modules itself. for the generation process, and I was looking at the loss functions that you were using. I was looking at the paper too.
Hmm.
So I was like kind of curious that like in general, like in flow matching, like we have this like velocity that's kind of predicted with, and there's like an ODE that's being integrated, and also with diffusion, either denoising or score. So but like here you are predicting the log likelihoods, like you have like heads that kind of predict the log likelihood for both of these modules separately. So I was kind of curious at how are they being coupled together, because they are like two different paradigms of generation and training, and they have their own like inherent like losses, velocity or denoising or energy or score kind of. So like how are they connected together? I was kind of unable to understand that.
So the in terms of the model itself, we don't actually need to change anything massive about SemlaFlow's backbone. The different modalities, because SemlaFlow requires that, or SemlaFlow is an E3 equivariant model, the invariant and equivariant components have to be treated with some degree of delicacy in the sense that they have to be passed through the model differently and they can only communicate with each other in a way that doesn't break equivariance. Um, but in terms of having multiple modules that are coupled to each other, you can see that this backbone is a single backbone that produces both, in the SemlaFlow case, atom predictions and bond predictions, but in the SynCoGen case, we simply replace the output heads to predict logits for our building blocks and reactions, and we leave the the atomic coordinate prediction uh, head as is. And so even though the losses are different, depending on if you're talking about coordinates or building blocks, the main backbone is only a single backbone, and it produces the outputs that are passed to the losses for all of the different modules. So once you have the coordinates and nodes and edges, you can easily calculate a log likelihood with the logits for the nodes and edges, and you can easily calculate MSE and pairwise distances and all of that for coordinates. Does that help answer your question?
Yeah, thank you so much. Yeah.
Yeah. Anyone else?
Oh, yeah, I have a question, very silly question, but the, because you saw many matrix and just curious some of them like the MMFF, what is that matrix? Like,
Oh, all of the um GFN, FF, all the FF correspond to different energies calculated via different sort of molecular force fields.
oh,
So all of these have different parameters that describe atom by atom or for the whole molecule, how high or low the energy of your generated molecule is. And you can see the down arrow just means that lower is better. So the lower
mhm.
energy of your generated molecule, as calculated using this particular force field method, the lower the energy, the better. And that just means that the atoms were placed better so that they're in a more like relaxed state. Because true molecules, obviously, they wouldn't be super high energy or have a high strain because of physics, I guess. So yeah, lower energy is better, and these just correspond to energies.
So yeah, so usually we assume that like one atom plays in one potential, so it should have a one like potential value. Why the MMFF and the GF and FF different? Why they are different? Like, do you
I
have?
think I think it just comes down to different force field parameters. I don't know too much about because Chung Hao, my collaborator, did most of
Mhm.
these metrics. He could probably answer this better than I could, but I think it just comes down to different parameterizations for our force field parameters. Um, But again, I don't know this too well.
Mhm.
Um, yeah,
Yeah, thank you.
yeah,
I'm wondering for losses, like it seems like the thresholded pairwise atomic distance loss and the auxiliary bond length and smooth LDDT loss, like they kind of have like similar information, like they're all related to like the internal geometry of like pairwise losses. Did
yeah.
you decide on using like the thresholded pairwise atomic distance loss as the main loss, like after trying different things? And it works the best for internal geometry.
hmm Um, I think honestly, I never tried swapping, like simply swapping out pairwise distance loss for smooth LDT loss because, and yeah, I'm aware that they basically encode the same information just with different like thresholds and smoothness. But I would, when I was doing the experiments for SynCoGen, I kind of treated it as an additional loss. So most of the experiments just included everything. So I didn't really replace pairwise with smooth LDT. We just threw all the different losses and saw how it went, just to just because we were curious, honestly.
Yeah, and when you put all of the losses together, especially like when some of them encode like same information, like did you have to tune like how much to scale each loss very carefully?
Yeah, we did. I think in particular, we if we did have the pairwise loss, we either wouldn't use smooth LDT or we would weight it very low because essentially if we kept smooth LDT with pairwise distance loss, we would have pairwise distance weighted double everything else. Um, and just in general, if we are using things like time weighting, um, terms like bond length losses relative to say MSE would be lower just because um, there's a little bit more forgiveness. It's a little bit more forgiving as you get into these smaller or higher time weightings. So we had to scale the losses accordingly so that one term wouldn't disappear relative to the other terms, and this was more of like an empirical thing than anything.
Okay, yeah, like intuitively, it would be safer to have MSC loss like weighted more at small noise level.
Yeah,
Is it like sigma weighted?
yes.
Okay.
All of our losses are weighted um, higher at lower noise levels.
Okay.
And this includes the graph loss, by the way. So there is a time weighting of graph loss that's sort of it's what the diffusion loss collapses to. And conveniently, it also has a time weighting, so we don't have to impose additional time weightings on the log likelihoods. But we impose 1 over t, so just a very simple 1 over t time weighting for both MSE and pairwise distance losses. We also tried t squared, but it's a little bit more unstable that way. The losses can kind of explode at very low levels, but we did try that.
Okay. Thank you.
hmm
Yeah, also another quick question. Like you mentioned, like it's trained for unconditional generation, but you also tried like conditional generation in cases where you do have a protein target, but you didn't encode like information about the protein pocket. Did you just like target via like pharmacophore matching? Like
So yeah, sorry.
like say you know places where, for example, there would be like a hydrogen bond donor and you just like fix that part and then diffuse other parts.
Yes. So what we did was because the problem with conditioning directly on proteins is with a synthesizable mo model like ours, it's difficult to decompose, say, the PDB into our building blocks or building blocks of our choice. So we lose kind of the access to um, ground truth sort of co-crystal structures of proteins and ligands. So to get around this, what we did with the pharmacophores, um, so first of all, I should clarify that the pharmacophore model is trained separately. It is a retraining of SynCoGen, but the fragment linking is not. And that's because the pharmacophore requires that we modify the backbone to incorporate conditioning information from pharmacophores generated by our molecules. And the goal with pharmacophore conditioned generation was if we can't directly condition on the protein pocket by using the PDB, we could instead take PDB co-crystal structures um, with a ligand, so a protein that had a ligand inside it, calculate the pharmacophores that that ligand had, and using our pharmacophore conditioned model, provide those pharmacophores to SynCoGen and generate a molecule in the same pose. So that's just one way we got around doing direct protein conditioning, using the reference ligand's pharmacophores to generate molecules in the same pose inside that protein as the reference ligand.
Okay, so this is more like for optimizing or finding analogs of existing protein small molecule binders instead of like kind of targeting protein targets that don't have binders.
Yes. Yes. And I think this is actually a pretty good use case for a model like SynCoGen, just because if you have a molecule that's very difficult to synthesize, it's definitely a worthwhile experiment to find an analog that recapitulates most of its pharmacophores or um, protein interacting sort of features while being much easier to make.
Yeah, do you think this kind of method would also work well for not natively co-crystallized protein ligand structures, but for example, like the conditional generated methods, like if you use like some diffusion model to generate like pocket to mole, and can you like would it still work well, or does it kind of have to be something like natively existing?
I think it would. I think it would always be better with native. Just yeah, just because if you're if you're trying to capture pharmacophore interactions that aren't real, then it's not um like you're not going to be any better than whatever molecule is generated. So if pocket to mole gives you a bad molecule, you're kind of at its mercy. You're generating something that's like a bad molecule. Um, which will also, of course, be a bad molecule and or in a bad binding pose. I think something that's a little bit more promising than using something like Pocket 2 Mol to generate hypotheses that then SynCoGen can generate analogs to is um, direct pharmacophore featureizations of the pocket. You can kind of reverse engineer what you want to bind to a pocket by looking at its geometry and sort of inferring what, like if there would be a hydrogen bond acceptor in a specific place with a specific radius here, or a hydrophobic interaction here, or a ring here, you can sort of reverse engineer like a molecular sort of cloud or hypothesis within that pocket. And I think that would be useful to target pockets that um, aren't necessarily filled with a native ligand, but are of interest to SynCoGen regardless.
Okay.
Yeah.
Do people have more questions?
So in this slide, you said adding auxiliary loss improve model performance slightly, but I think you do ablation study and you saw that it improved like by the large margin that in the ablation study.
Yeah. I think it's more significant than other improvements like scaled noise. Didn't really You don't even have to know what that is. It's not particularly important, but um I would say I guess I should say the improvement was somewhat moderate. Uh I would say that the most improvement we got was from adding constraints and from adding self-conditioning. In practice, auxiliary losses was something that we did only after all of the fundamental improvements were in place to try and push the performance by another like 1 or 2%, validity wise and just energy wise.
But it's a auxiliary log is 80. Like I don't understand. It's like 85 minus 69, right? Oh, you add
Oh,
auxiliary loss and
it's 93 minus 85
93. Still
because it
8%. Yeah.
yeah the I guess the way that this graphic should be read is the base model includes everything, and each one down is the performance after you remove the method on the left. So minus inference annealing, GFNFF goes up a little bit. Minus auxiliary loss, validity goes down from 85 to 9 to goes down from 93.5 to 85.3.
I see. Yeah. Thank you.
Yeah.
Oh, what are the constraints here for the ablation?
They are these. So compatibility constraints, making sure that if we denoise a reaction, all the building blocks are compatible that are adjacent to it or that it defines are the outgoing and incoming building block. And for building blocks, the reactions that are denoised near it have to be compatible with its reaction centers. And also the edge limit constraint, like these constraints.
Okay, got it.
Yeah.
Yeah, if people don't have more questions, then I think we'll end here. Okay. Yeah, thank you so much for presenting.
Yeah. Thank you so much for having me. It was great to present here. Feel free to check out the model and GitHub if you guys are interested, and hopefully I'll see you guys in future talks.
Yeah, see you.
Thank you.